MBA633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. We'll continue our discussion of probability, and this clip will focus specifically on the binomial distribution. It is a pattern of uncertainty for a discrete random variable that arises when the underlying experiment meets certain very specific characteristics. So let's introduce that distribution with an example. So a university found that, based on historical data, 20% of students dropped the introductory undergraduate statistics course by the last drop date. So in fall 2012, 40 students are registered for the course. What is the probability that exactly 3 students will withdraw from the course by the drop date? And second part is, what is the probability that at most 3 students will drop the course? Now, if you think of the random variable x, which represents the possible outcomes of this experiment, you can see, if you think about it, that this experiment yields a discrete random variable with 41 outcomes. If x represents the number of students who withdraw, then x can take any integer value from 0 to 41. I'm sorry, 0 to 40. 0 to 40 because and that results in 41 outcomes. Okay, so this is a discrete random variable. So the issue is, what is each of those probabilities? What is the probability of x equal to 0, of x equal to 1, x equal to 2, and so forth, all the way up to x equal to 40. Now you remember from our discussion of discrete random variables that each of these spikes, in other words the height of each of these spikes, the probabilities, each of those spikes must be greater than or equal to 0 in height, and if you add up all the spikes, then they must add up to 1. So all the probabilities from 0, x equal to 0 to x equal to 40 must add up to 1. The issue is, can I systematically find the height of any one spike? So in our case, I want specifically probability of x equal to 3. What is the probability that exactly 3 students will drop from the course? So I want the likelihood, I want the height of the spike for x equal to 3. So let's see if we can estimate that precisely in a systematic way based on the characteristics of the experiment. Okay, so if I use the letter W to represent the fact that a student withdraw and R to represent a student who remained in the class, then if I have the following sequence of outcomes: withdrew, 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 okay, followed by 37 R's. All right, let's see here, followed by 37 R's. So R all the way up to 37 R's. So this is a sequence of student decisions which results in 3 students withdrawing. However, I could also have the following: the first student remains, okay, the next 3 withdraw, and the remaining 36 remain. Right? So there are many different combinations. So I could have the first 2 remain, the next 3 withdraw, and the remainder again stay back in the class. So there are many different sequences, all of which meet the requirement that 3 students have withdrawn. So let's see what is the likelihood of any one of these sequences. The likelihood that the first 3 students withdrew is simply 0.2 to the 3. Why? Because we will assume here that the outcomes are independent, the trials are independent. In other words, that whether or not the first student withdraws has nothing to do with whether or not the second student withdraws, and with the third student, and so forth. That's an assumption, okay, that has to hold true in order for the binomial distribution to result. All right. So if the trials, in this case, for example, each trial consists of a student either staying or withdrawing. So you remember our discussion of independent events. If you have 2 events, they're independent. If they're independent, then the probability that those two events happen at the same time, in other words, the joint probability, is simply the product of their own probabilities. Okay, so the likelihood of 3 students withdrawing, the WWW, the first 3 students withdrawing, assuming that their staying or withdrawing is independent of one another, is simply 0.2 to the 3. So followed that by the probability of 37 students remaining in the class is simply 0.8 to the 37. Okay, by the same logic. Now, if I look at the second sequence, if you think about it a bit, it is 0.8 times 0.2 to the 3 times 0.8 to the 36, which is the same as saying this is also 0.2 to the 3 times 0.8 to the 37. So each of these sequences, okay, each of these sequences, the probability is 0.2 to the 3 times 0.8 to the 37. So the only remaining issue is how many of these sequences can I have, all of which have 3 W's and 37 R's. So here we make use of our factorials, permutations and combinations, if you remember. So if I have 40 items, then the number of ways in which I can arrange 40 items is simply 40 factorial. That's permutation of 40 things, right? So I have 40 students, so the way I can arrange 40 of them is factorial 40. However, 3 of them are same. 3 are W's, right? So in how many ways can I arrange 3 W's? Is factorial 3 ways, right? So if I swap the W's among themselves, I wouldn't get any different sequence. So I have to reduce the 40 factorial by the number of ways in which I can arrange 3 of them. Similarly, the number of ways in which I can rearrange 37 R's is simply 37 factorial. Okay, so the number of different sequences that of these 40 students, all of which results in 3 students withdrawing and 37 staying, is given by 40 factorial divided by 3 factorial multiplied by 37 factorial. Now, if you recall our definition of combinations, I think you should recognize this to be 40C3, combination of 40 things taken 3 at a time, with the number of ways in which you can pick 3 things out of 40. Okay, so now we can piece together a complete probability. The probability of exactly 3 students withdrawing from the course is simply 40C3 times 0.2 to the 3 times 0.8 to the 37. Okay, so now if I want the height of x equal to 4, probability of 4 students leaving, this would simply be 40C4 times 0.2 to the 4 times 0.8 to the 36. You get the picture now. Okay, so in general, the probability of x successes, small x successes, is simply 40cx times 0.2 to the x times 1 minus 0.2, which is 0.8 basically. I'm writing this 1 minus 0.2 to the power 40 minus x. Okay. Fortunately, there's a built-in function in Excel to calculate this for us. We don't have to do this manually. So let me show that what that would be for you. Okay, so let me show that it would be equal to binom. So it's binomial distribution, and you say, okay, how many successes am I looking for? I'm looking for 3 students to withdraw from the course. There are a total of 40 students in the course. The likelihood of any one student leaving is 0.2, and I want the probability of exactly 3 students leaving. So this last parameter that I'm going to write is either a 0 or a 1. So if I want the likelihood of exactly 3 students leaving, in other words, the height of only the spike x equal to 3, I'll put a 0 over here. If I wanted the probability of at most 3 students leaving, then I would put a 1. That's called a cumulative probability. Okay, so oh, looks like I mistyped the name, so I got to type binomial dist. Okay, and the probability is 0.02. So the likelihood of exactly 3 students leaving is 0.0205. Now the second part of the question is, what is the probability that at most 3 students will leave? So you can see that is the probability of x equal to 0 plus x equal to 1 plus x equal to 2 plus x equal to 3, and that can be easily computed by simply taking this same binomial distribution formula and changing that last 0 to a 1. That's called a cumulative probability. Okay, in other words, the cumulative of x equal to 0, x equal to 1, x equal to 2, x equal to 3, and we should definitely get a number that is larger than 0.02. So we come up with, so it's 0.028. It's larger than the previous number that you saw. Okay, so this is how you would compute the binomial probabilities. Let me change this back to a 0. 0. Okay, so you can see it's gone back to 0.0205. So the probability of exactly 3 students leaving is 0.0205. The probability of at most 3 students leaving is 0.028, if you remember. Okay, so this is what a binomial distribution looks like, and this is how one goes about computing it, and there's a built-in function in Excel to do just that. So you have a binomial distribution when the experiment meets the following criteria. The experiment must consist of n repeated trials, in other words, running the same thing n different times. In our case, that trial is for each student whether they stay or leave. Okay, so you can see that each trial consists of exactly 2 outcomes, whether they stay or leave, and we are asking the same question of the 40 students. So the experiment consists of n repeated trials. The trials are independent. Whether one student stays or leaves has nothing to do with the next student staying or leaving. And the probability of success, in our case success, defined a little bit perversely, is a student leaving the course. The probability of success remains the same from trial to trial, so it's always 0.2 for each student. So if an experiment meets all 4 characteristics, then they're listed here, then the pattern of uncertainty that results from the underlying random variable is a binomial distribution.